Last day, I believe the last thing I left off with was core notation. That ring bells? Excellent. So, 2 new words from last day, isoelectronic, and then substituting in core notation. Did we finish core notation? Oh, I had to see them before you left. Let's call in a couple people to show me what those look like. Sorry, hosting. Okay. Dojo. A. Attendance. Brooklyn. Kaylee. Chet. Davis. No Davis. Denzi. Dylan. No Dylan. Francois. Heather. Jaden is here. Jonah. There you go. Kate. No. Oh, right. I still have to fix that. Lillian's here. Lucy is not here and hasn't been for a while. Mimi. Thank you. Sabina. Nope. Simon. Nope. Thomas. Cool. And Valerie and Veer. There we go. So just to remind us from last day, Veer, what was chlorine to the -1? In square brackets, yep. And I'm going to get out of everybody's way. Francois, why are you late? Yeah. That's not a good reason at all. That's a terrible reason. 3S2. 3P6. Excellent. Brooklyn. Yttrium. You would have had it yesterday. Or last day. Oh, dear. Well, find yttrium on your periodic table. Yttrium is right there. Got your periodic table out? Excellent. What's the noble gas before it? Yeah. So if you go this way and then go back up one, what's that noble gas? I think you went up too far. It is 1, 2, 3, 4 down. Krypton. Superman. So rather than going 1s2, 2s2, 2p6, 3s2, 3p6, we can just say, and hold it. We can just say square bracket Krypton. And that way, all of that is just taken as read. So if that was krypton, and here we are with yttrium, we erase all this. What's left to do in this row? Five S2. And then what's that one? The one yttrium is in. How many in is it of the D's? 1. So 5s2, 4d1. Hold it. No, I lost track of my own. 5s2, 4d1. So core notation allows you to skip all of the previous stuff and just put in what is the valence electrons. Nope. Valence electrons. Because that's what we're going to have to do next. The topic immediately after this is going to be Lewis dot diagrams. Here, let me move this over. And I would like you, in pencil, to give me the electronic structure of gallium. Gallium plus 1. And then gallium plus 3. And while you're doing that, I'm going to quickly put in the absences because there are a lot. Sorry there. There. Brooklyn, Dylan, Simon, Kelly, Sabine, Heather Valley, Jaden, Thomas, Pat, Chip, Leah, and Lily. Perfect. Okay. Okay. Using core notation. No, just give me the electronic structure. And I'm going to add one now. I'm going to add vanadium. And I'm probably going to focus on just gallium and vanadium first, now that I think about it. So, Heather, what's gallium? Yep. 4s2, 3d10, 4p1. Right? No, that's good. Yeah. Because this is just the electron structure. All good. And Mimi. Oh, Francois, yes. Oh, were you here last day? Yeah. Ah, core notation. You were also late to this class, so you missed the mini review. He says, letting the guilt hang heavily over him. So when we write electronic structure, what we can do is, instead of writing out the entire electronic structure, we can take the electronic structure of the previous noble gas. So not the noble gas in the same row it's in, but the previous one. So the structure of helium is 1s2. So you can substitute helium in for 1s2 for these three. The other thing we did last day is that these are isoelectronic because they all have the same electronic structure, O minus 2, added 2 electrons, neon and fluorine where you add 1 electron. Now for this, it doesn't save very much. But for chlorine, you save 1s2, 2s2, 2p6 because you just say, oh, neon. So find chlorine on there and then find neon. Do you see how we substituted that in? Now, does that make sense now? Excellent. I'll probably ask you the next question. Except I already asked Mimi for vanadium. Yeah. Argon 4s2 3d how many? Right. So I'm going to pick on Francois then. Francois, how many valence electrons does this have? How did you get 20? I don't think there's any atom that has, well, and the ones that have 32 theoretically. But so the core is this. So you don't have to count any of those. How many electrons are here? No, but they're not filled. That D subshell is not full, so it's still higher in energy. So it'd be 5. Yeah, are you reading the sentence down below? Because if you were, that was clever. This isn't full, so there are 5 valence electrons. But if you keep going, how many valence electrons are there in here? 3. Because this one is full. And once it's full, what energy level is it at? Just say it. 3. So it's in the third energy level. The valence electrons are only the fourth energy level. Once it's full, it drops below. Heather, you look pained. So another one is one I did last year to do it on the periodic table, because that's a little arcane. If you remember the trick from last year, I would say, how many valence electrons are in nitrogen? And what would you do? You'd count from where? Yeah, to the left. You just go here. So how many valence electrons are in nitrogen? 5. So you go 1, 2, 3, 4, 5. And we're doing the same thing, because this is just 2s2, 2p3, and you go 2 plus 3 is 5. So same thing. And if I said, how many valence electrons are in sulfur, Heather? 6. 1, 2, 3, 4, 5, 6. And then if I, I said, Kaylee, how many valence electrons are in calcium? 2. But then I go, how many valence electrons are in selenium? What was the rule? You ignore. So Kaylee, how many valence electrons would be in selenium? 6. Same as oxygen, same as sulfur. So you go 1, 2, skip a few, 3, 4, 5, 6. That was the rule I taught last year, and I didn't explain why. And the reason is because you're counting up 4s2, 4p4, 2 plus 4 is 6. And these are, now we know that these are not 4 level 4 energy levels, it's level 3. And once it's full, it goes back down to join level 3. This is the 3D, not the 4D. The 4D is all the way down here. So it drops down an energy level, and you don't count it anymore because it's full. But when it's not full, if I said how many valence electrons, and I didn't do this very much last year, if I said how many valence electrons are in titanium, you can't skip. How many valence electrons are in titanium? So, what? Sorry? Oh, I thought you said something, but it was at the edge of my hearing. Pardon? 4. 1, 2, 3, 4. As long as you're in the row, you still have to count them. So the number of valence electrons in zinc yes? 12. It's a lot of valence electrons. Now, there's still some funny business that goes on. This 3D does sink a little bit, so it will actually become a +2 island because we move those first. We'll show that in a minute. But in terms of counting valence electrons, you skip it once it's full. And so zinc does have 12. It's on the edge. But gallium has 3. Now, if you want to know why, it's easy. It's because it's quantum. In a practical way, there's only 2 forces going on. There's the as for all our trends, the attraction of the nucleus to the electrons. And down here in the transition metals, the attraction is so strong, the electrons are moving at near the speed of light. The attraction is huge. And then the other force is the repulsion of the electrons to each other, with all of those complex shapes thrown in. So they're being repulsed in different ways. So they're not just nice, even shells. You've got, butterflies and dumbbells and everything repelling everything out there. So this rule that we fill up and then we say, oh, well, this drops in energy level, that's not just something we say, that's something we observe, because we'll take a spectrographic analysis and we'll look at where the electrons are and we'll say, these electrons have actually dropped down. So that's why it fills up that way. Why does it drop down? We don't know really, other than it seems happy when it's full, completely full. And you start filling the next one, and that one just goes woo. Wait till you see the exceptions. So, using that, I'm going to take that away. Ooh, I can't. Ooh. How would we change that to make it gallium plus 1? Kaylee. You just take out the 4p1. You take away the latest electron. Gallium, oops, I lost, looks like I lost the other bracket. If I was now to become gallium plus 3, and I've gotten rid of 1. And this is a bit of a trick question, although not really, but thinking about what happened once it was full. Lillian. Oh, we're at plus 3, so we have to take away a total of 3 electrons. We've taken away 1. Where do we take away the next 2? 4s2. Yeah, so the 3d10 just sits there. Nope. It's not included in the square notation, so we have to keep it. And we keep it. And that's why the 2 most common ions for gallium is plus 1 and plus 3, because it can get rid of its p orbital, and boom, that's a fairly stable state. You've got 2 full orbitals. That's great. In addition, it can get rid of its s orbitals. They're next. And now we just have the d10s, which are down in the 3rd level as well. This is a really stable ion. This is the most common ion. It loves being gallium plus 3. Yes? Because we always write it in the order that we filled it, not the order of their energy levels, because their energy levels can change. So for all the Ds, they're 1 level less. So we go, this is 1s, 2p, 3d, 4f. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. And then we go through all the 3ds. And until they're full and we're across, it's part of the valence electrons. But once it's full and we start moving away, then it drops down in energy level. So we take the electrons away in a different order. So a couple of definitions. Valence electrons are those not in the core and not in filled DF subshells. And when we're looking at electronic structure and positive ions, a useful way to remember it, P before S before D. So we remove p orbitals before s orbitals before d orbitals. If we had gallium plus 4, we would start removing from the d. I don't think there is a gallium plus 4. That would be very rare. Yes? Pardon? Isn't the core? Yeah, the core is all the previous electrons. So like the one where you use like argon or whatever to summarize it, those are never part of the valence electrons. And then the valence electrons, if you fill a d shell, then those aren't part of the valence electrons. Although we still write them into the electronic structure because they're in that level. And I'll write it out a little bit more succinctly. And you can write it either way depending on how you remember it. Yeah, my mouse. So, some examples. Let's do tin. 10 plus 4. 10 plus 2. And if you want to remember the symbol for tin, you can remember that the Latin name is something along the line of stannis. But I remember it because tin is a sin. Oh, use core notation. So you have to put the nearest noble gas first. You always have to put that first. Excellent. Where's tin? Oh, well. You have in your periodic table an alphabetical list. So find tin. Oh, what number is it? So then you can pop back over. Element 50. There you go. Yes. Always remember there's an alphabetical side to your periodic table. Yep, starting well. Excellent. Starting well. Starting off. Nice. Well, you have to know something because you managed to get this far. What now? You erased that one. What did it start off with? Okay, hold it. Where's your periodic table? pull that out. Never leave it in your book. You're going to need that. Every class. And then show me where tin is. Excellent. So what's the nearest noble gas? You got that, it looks like, because you got krypton. So when you go to the next row, what does it start off with? What orbital is these two? Yeah, it's s orbital. And then count down, what number is it? All the way down to the row that tin is in. 4. So 1, 2, 3. I think you miscounted. Count from the beginning again. 5. So the first one you put down would be. Yeah. Yeah. So erase that. Let's just do plain old tin. Excellent. Now keep going until you get all the way up to tin. So you had 5s2. What's the next one? Yep. Yep. How many? You have to count along. How many are there in the D? Use your periodic table because that's a reference, but you're going to have to use this. Oh, the D's, and yeah, it ends there. So this box from there to there is the D's. So yeah, 4D10. And then what one's next? Yeah. How many over is it? Count. Yeah. Yeah. So then rewrite that for these and then figure out which 4 do I remove, and then for this one, rewrite it the original, and which 2 do I remove. Okay? Here we go. I'm going to check there. There was someone at the beginning I think I needed to check. Fear, you got that? Yep. Now, the next 2. Rewrite it out and then figure out which ones you need to remove. Same. You've got that one, but you need to rewrite it out and figure out which ones to remove. Nice. Where's your period? You got your period table, and then notes from last day. Pull that out. That's a useful chart. Because if you're still looking at the chart, then that's a useful chart to have. So you've got that correct, and then how many along is that one? So in here, where is it? Right, so you're here, you've done 4s or 5s2. So what is this? This row in the middle. Yeah, and how many are there? And in this case, you just literally count. Start at the beginning and count. Oh, no. The D's end here. So D only goes from in the blue section. Yeah. And then what's this one? So what's this core? 5p. And how many over is it? 2. Excellent. Now rewrite that for both of those because it's going to be the same. You're just going to remove some electrons. How about yourself? Excellent. So rewrite it for the next 2, and then then you just erase the ones you think you should remove. Write it out. Take a guess. Use the rule. Yep. Would what? Oh, I'm not going to tell you yet. I'm going to do that on the board. But I want you to try it in some way. So it's good that you are doing it. You have 4F. How'd you get F orbitals? Oh, no. Because this doesn't have everything. I only use this for examples up to there. and it's missing the some later ones. Like it's missing the 5p, for example. So don't use this. You don't have the handout. Right. So let's do that again. You will always have access to your periodic table, and it's helpful to think of this block. We include helium in that block as the s orbital. So that starts off with 1s, and then there's 2s, 3s, 4s, 5s, 6s, 7s, and so on. This block from here to there, it's the blue section, is the d's. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this block is the p's. Doesn't include helium. Now it starts with the 1s, 2p, and 3d. So if I wanted the electronic structure of like chromium, I would go 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6, 3s2, 3p6, 4s2, and then chromium's there, 3d, 1, 2, 3, 4. And you just count it along. Does that make sense? So let's do it for tin. Now, we're using core notation, so we just go to the nearest previous noble gas. So write that, yep. So you've got that. And then counting along from here, what S is this? 5S? Yep. Perfect. No, you can't skip them for writing them down. So you still have to write them down. We skip them for counting valence electrons, but we don't skip them for electronic structure. Yep. 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 Hold it. Why 4p? That starts at 2p. 1, 2, 3. So that is 5p. Sure. Well, when we did the orbitals of the different types, the first energy level had only s. The second energy level had S and P. So S and P starts at the second energy level. So it starts at 2. The third energy level had S, P, and D. So those are all 3. Except we don't fill up the 3Ds until after we filled up the fourth S. Yeah. Yeah. And if you even went to here, it'd be, because this is 4F. And you don't start filling it until you're at the 1, 2, 3, 4, 5, 6S. So it goes 6S2, 4F, 14, and then 1, 2, 3, 3D, 10, and then you would continue on with your 6P. We won't do anything in there, but the other way is just, and remember, it's 1, 2, 3. It's on the videos, but if you email me, I can add it to the notes in the classroom because we're going to be finished it up today. And then just rewrite it for the other 2. And then you have to choose what electrons to take off. Denzi. Tin. R. Pardon? KR. Excellent. Sorry, my ears. KR. Excellent. Now I'm just going to write this right away because the next question is, which ones do you remove? 1 second, hosting. Okay, for 10 plus 4, Jaden. That is for normal tin. That's that one. But if we were going to have 10 plus 4, using this rule, what would you remove first? Yeah. How many are in P? 2. So we take out those 2. That's an awfully big eraser. And then we have to take out 2 more. So where would you take out the next 2? 5s2. So we take it out there. So it's krypton 4010. Now if we had to only remove 2, who needs more points? Lillian. What would you say for 10 plus 2? Yeah. So we're still taking off the outermost one. If we only take off 2, we take off the P's. But if we have to go beyond that, we skip the full D's into here. Now, for some reason, we found like a 10 plus 6 ion. Then we would start pulling from the D's. But that will almost never happen. Hold it. Apparently, I forgot to plug in my laptop, and it's about to shut down. Oh, please don't shut down before I get this plugged in. I like how they phrase it so politely now. Your PC battery is running low. You might want to plug in your PC. Why, thank you for that. Okay. One more thing for today. I think we got everything else here. Yeah, we did that. And next, probably just use that page. Is we're going to do exceptions. Why don't I type it? That would make it easier to read for everybody. Oh, one thing, only because I learned it last night. It's not particularly important at this point that we know the name for this, but this process of filling them up in order is known as the Offbow Principle. So if you were looking online and you want like, oh, I want some more practice of this, you want examples of the Offbow Principle. Offbow, it's German. I think it means like building a foundation. Yeah? That would make sense because you're building it from the bottom up. So it's not someone's name, it's actually descriptive if you speak German. And this is exceptions to electronic structures, specifically exceptions to the Offbow principle. And for that, the two most famous exceptions are copper and chromium. And I would like you to give me the electronic structure of copper and chromium, assuming they're working as per normal. Use core notation. Heather? Sorry, I thought you were about to say something and interrupted you. No? Okay. Yep, right there. I'm just going to come back and check. Sorry, I just kicked your bag. No. Why not? Because it's in the same row. Where's copper? Right. So, yeah, it'd be that one. Excellent. On your way. Looks like you're working it out. How are you doing? Yep. 4S. And then, yeah. Oh, I'm not going to tell you. You can check with someone around you. But you are doing it. It does look like you're working through. Looks like you're working through. Oh, sorry. I was looking at these, and I'm like, it's not completely full. Yes. Excellent. 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 And you've got them down. And I think I've already checked yours. Just going to walk backwards. Excellent. Now, the next one. Good. How are yours? 9, 3, 4. Excellent. Okay. Copper. Random. Come on, random. Oop. Chet. AR. Yep. And chromium. Francois. Now, they found that when they did spectrographic analysis, that this is not their electronic structure. Turns out, I'm going to write this down below. Half full. Oh, I don't need it bold and underlined and italicized. So, There we go. How did it? Unfull? Is that a word? Unfull. We'll go with unfull. Unfilled? That sounds better, but I'm really kind of partial to unfull now. But unfilled sounds a lot. Unfilled D shells that are not half full are particularly unstable. I don't know how to write that in less words. That's a long sentence. Unfilled D shells that are not half full are particularly unstable. They don't like being partially full. So remember, they want to fill up and then subside and go down to their brethren in the third energy level. They're really up high. Their friends are all, pardon? Oh, yes. Sorry. And I could probably also do this. So this is the explanation for what I'm about to do. However, knowing that, and you have all these electrons to play around with, what could you do? Is there a configuration, and if you moved electrons around, that would be more stable? They won't go into the P. They have to. They're in the S and the D. Because the P is the next level up, so they're not going to gain more energy. That would be exhausting. But right now, that D shell is not full, and they're not half full, so that is particularly unstable. Kaylee? No. Say no. Please say. Yes. How many S electrons? One of them. Perfect. If you take one electron and move it over, then you get 4s1 3d10. And now the first energy level is half full because it only has 2 to begin with. It's fine. The second energy level is completely full. And it's really happy. So that, and if you do spectro analysis on this and try and figure out where these orbitals are, that's the structure you get. Same for this one. One electron goes over, and you get 4s1 3d5. And did I put it down? Oh, did I put it down here anywhere? Now, these are exceptions. This isn't a rule. And what I mean by that's not a rule is now that you just learned this fantastic trend, does tungsten do that? Because it's got 1, 2, 3, 4, 5, 6, 6s2, 5d4. So you might be tempted to think, and obviously I'm setting up that the answer is going to be no, that it will jump off. And the answer is tungsten doesn't do that. Chromium does. Tungsten doesn't. And this goes back to that there's two forces in here. The force of the attraction of the nucleus to the electrons, which at this point are moving near the speed of light. because there are so many protons in here, 74 compared to 24. It's got 3 times as many. So it's trying to pull on them very tightly, and they're moving very fast. And you have the repulsion between the electrons, and there's a lot more electrons. And then it doesn't try to figure out, just the most efficient thing happens. It's like if you want to figure out the most efficient packing for a bunch of marbles, and you place them down deliberately, or you just take the bag and you shake them and they just find it out. We just shake it and the electrons fall where they may, and this one doesn't do the exception. There are more exceptions than chromium and copper, and I'm only going to require you to know those 2. So there are other ones here that do it, and there's ones on here that don't. And there is no hard rule, because both the Offbow Principle, which we're going up where you fill it up in order, and these exceptions, we come up with reasons for them, but it's actually just down to those 2 forces and what the individual marbles floating around the nucleus decide to do, because just what's more efficient. It's a really complex system, and our prediction abilities of what it's going to do aren't predictive enough to say that this rule works all the time. Our rules are just to help us remember, as opposed to that these are not mathematical rules. They're not true all the time. So I want you to know the exceptions for these. I will ask you for the exceptions of these when you get your test next week, and I'm going to ask you for like at least 2 electronic structures. One of them is guaranteed to be copper or chromium, because I want to see if you remember the exception. But I'm not going to expect you to guess. So if I say, give me silver, I'll expect 4D9, not 4D 10, and then you took one out of there, because you don't know if that's an exception or not. To be honest, I don't know. There's a list that you can look up, and like, this is an exception, and we determined it experimentally, and that one is, and this one isn't, and it's random. These are the 2 most famous exceptions, because these elements we use all the time in chemistry, and so these are important to know later on. And they're ones that you'll see if you go on and look online and you're like, exceptions to electronic structure, they'll always show you copper and chromium. Because even among the exceptions later on, sometimes they're exceptions and sometimes they're not. In some characteristics, they won't do that. So this rule is to help you remember these exceptions. It's not true in every case. So there can be cases where you have a structure like this and it doesn't move. That's just the way it is. Some chemistry teachers, so I don't know what Mr. Snow's teaching this year, but some chemistry teachers, because they want you to remember the rule. So if you talk to other classes, they might say, actually, all of these are our exceptions. And so that teacher has just decided they wanted to make the rule consistent. It's a bit of a lie, because tungsten definitely isn't an exception. And they'll say, the entire row's, and it's not. Gold definitely isn't. Silver actually might be, now that I think about it, but anyway. So they might do that. They might learn exceptions you don't know. You know why it's not. The rules will be consistent within the class that we're going to do, because I'm not going to make you sit down and memorize an entire list of 9 exceptions, because that would be silly. But 2, to exemplify the point, in case you take quantum chemistry in the future, the most famous 2 would be good. We are now done quantum chemistry. Somebody in one of the beginning classes, don't know if it was in this class or not, said, Mr. Neufeld, we want review sheets. And I said, no, because you have your entire Hebden list and all of your notes. And then I said, okay. And I made one. This review sheet is not exhaustive. It doesn't have everything on it. It has important things on it. Are there important things that are not on it? Probably, because I don't put absolutely everything on it, but it's a good starting point. If you work through this and you're like, I know all of those things, then you're doing pretty good. If you go through this and I don't know this thing, you shouldn't think of then if you know that one thing you know. You should go back to that area and review the area. So it's more like these are signposts. There is a 3-hole punch that should be coming around, because I didn't get a 3-hole punch before I brought it down. You have, I'm not going to do anything more now. It's 9:16. We have until 9:35. You can start now doing your Hempden, starting your own review, organizing your notes, catching up on any material if you're away. What day is our test? All Hebdens, once I'm done with them, if you aren't back on the day, they just go in here. So just come and check. Who do I still have here? Valerie? Yeah. I threw Yoggers on the ground. Sahage. Denzi. Brooklyn. Sasha's not in this class. Jacob. So. Always grab those. Clever. There is. I'm not going to post it. Yeah, that's what I'll do. So later on, after you have time to do it, I'll post the answers. But what I'd rather, what's far more useful to do, is studying alone with a review sheet is not as efficient as studying with someone with a review sheet. Even if you work on it separately, get together to compare your answers. The most fruitful discussion is when you both have something that's different and you have to figure out why. I had the most entertaining weekend listening to two students yell about pre-calculus 12. Well, 4 students debating what an extending was. Such conversations as, no, Mr. Warner's the boss. This is what an extending is. No, I got it straight for Mr. Norman. And then they're arguing over their answers. It was brilliant. Oh, and I've already noticed a mistake. 1B. Draw the structures of an S, px, and dz squared orbital. Or you could make it dx squared minus y squared, or you can make it any particular d orbital as long as you know which one it is. But there is no such thing as a dx squared orbital, so that as written is wrong. Z squared. I gave you a specific one. But that's just to remind you, you should be able to recognize the d orbitals. Those are the sp and d orbitals. So 1b asks you to draw them. Oh, the axes. X, Y, and Z, like the number plane. Each one of them had a name, so there's a PX, PY, and PZ. You have to be able to recognize the D. Yeah. So that forces you to go back to the D and see them all again. Yeah. Yeah. Oh, now, I posted it last night. When's our test? Tuesday, November 9th. The other E-Block class has to make a decision. I've currently scheduled it for them for Wednesday, but it's a shorter class. They have to choose, do they want to come in at 9 a.m. on a Wednesday, or do they want it first thing Monday morning? You would choose Monday? Oh, I see. I was not expecting that because in a different class, 2 students were like, obviously Wednesday. Obviously. Yeah, I think they were more like, I want more time to prepare. You're up by 9 anyway. Like, you're not sleeping. Like, you still have to get up for breakfast at 8. You just have way more time on a Wednesday. That way? Has it gone that way? Ah. Has everybody had the 3-hole punch? Then I will grab it and put it up on the front. Yes. Yes. So you need to know you're going to get a periodic table that's fresh. So exactly like the one you have, but a brand new one. So it's not going to have your writing on it. So you need to either be able to recreate that or label that on your new periodic table right away. Now in terms of doing it, if you just remember 1s, 2p, 3d, that pretty much sets you up, because then you can go 2s, 3s, 4s, 3d, 4d, 5d. You can, boom. But yeah, you do need to know that. You also need to know the trends. Are the trends not on there? I thought I saw ionization energy on there. Oh, the word trends is not on there. It's also missing Henway. Pardon? Yeah. Are you asking what's a Henway? It's about 2 kilograms. A hen. Wait, okay. It will tell you. So I could say without core notation to make sure you can write the whole thing, or I could say with core notation so I can see that you know how to do core notation. Oh, right, then Hobbes' choice. Actually, I don't even know what Hobbes' choice means. I should probably look that up. Turn out it means something bad. Predict the electron configuration. Oh, that's one is. Have you looked up the answer just to check? Because in this section, what are they doing right before it? Right. So that's what they're asking me for. Yeah. Yeah. So no core notation from the beginning, right? Yeah. So this, I mean, obviously the next question, they're going to tell you to use core notation. This is it without core notation. So go back to the question. So how would you do phosphorus? Phosphorus is right there. But we start at the beginning. Oh no, 1s2, but then you keep going. What's that one? Yeah, you just keep going along like that. Francois, what are you doing? What are you doing? Oh, you could. Oh, okay. Oh, why don't you study for it then? Are you just girding yourself for the onslaught ahead? Oh. Sorry, Heather. I told you Hobbes' choice. That is not the right expression. Hobbes' choice is when you have the illusion of a choice, but really you end up doing what you have to do anyway. Yeah. It's most often used by magicians, now that I remember it. No, yeah, that would be it. But it really is a free choice. You can choose to use it because it's a review. So if you were doing review properly, what would you then do? Yeah, it would. One is one and one is the other, and compare with someone else. Yeah. How is it arranged? there's an answer, and then you'd have to explain it. Well, that's an open-ended question, and there's lots of right answers, and and when you compare with someone else specifically, and they have a different answer, so you could say it's arranged by metallic character. You could say it's arranged by any of the trends. Actually, you could say, it's arranged by atomic number, by increasing number of protons, but obviously it's also arranged by electronic structure. So there's lots of different ways to answer that question. Now on your test, you're still going to see marks beside every question. And I generate, as you know, 2 sets of marks. One goes into the magic spreadsheet. And then each question doesn't have marks. It just has proficiencies, extending, proficient, that sort of thing. And then the other one, you generate your traditional mark, which goes into my traditional spreadsheet, so I can compare what you're getting, so you're not being cheated. If you're doing it on the non-traditional one, the new one, the number of marks should just indicate the depth in which I'm looking for. One of the things I've noticed in the new curriculum, it's not really a new curriculum, a new method of marking, is that students overcompensate and they try and write everything down. Like you just generate more and more and more, and that's not really the point. If it says 2 marks, I'm not expecting a lot. Yeah, I think that's one of the problems with the new ones, is that more is not really better. Some of the best answers are short, but they're well done. It's like, yes. But more can get you there, because if you're not saying it like the right things, but you're not saying wrong things, sometimes you manage to babble your way to the right answer. It's not really extending, but you get proficient at least. You're trying your best. Yeah. I don't know, does the new system make you less panicked or more panicked on a test? Okay. Fair. There's a lot more, yeah, and there's more so I mark it traditionally. I'll mark it with the proficiency. I'll put both of them in. I've got 2 mark books. I've just made it, if you get 100%, you have extending. Because it is impossible to get above 100%, because 100% represents the maximum that you can get. Yeah, that doesn't. Oh, I thought you were coming up for a question. Ah. You're throwing away notes as part of your... Interesting. Oh. Oh, cool. Extra study notes from the lab? They can go recycling. There you go. Oh, and I probably don't need to keep